So this is a great problem because it forces you to think about how velocity, acceleration, the derivative and second derivative, how all that is related to each other. So remember that when we think of velocity, that's the first derivative, and acceleration is the second derivative. So that's going to help us a little bit figure out. So the goal here is we have several different graphs, and they show the position of a particle moving along. It's as a function of time. So here this guy is the x-axis is time, and the y-axis is the position. So for example, in this first example, this first particle, it's going here is its starting point. It goes further away from its starting point, and then here it's back at the starting point again, and then here it's back again as its starting point. So it's kind of like you go forward and then you go backwards, and then you continue to go backwards, and then you go forwards again, and you end up at exactly the same spot. Here you start, so if you think of this as position 0, it's important to realize that when you are moving positive, this is kind of like you're moving in the positive direction. So this is kind of like you're moving to the right, and now when you're moving to the left, that's in the negative direction. So here, what this is saying, if this, it doesn't matter what number this is, but for example, let's say this is -4. So that would mean that you start to the left of the, what you're considering 0, your starting point. And then you're going forward and forward, and you end up past the starting point, starting position, for this guy. So we'll talk about all of these, as we go along. So the first thing is, let's look at A says, okay, which one of these has constant velocity? Okay, so again, velocity, remember, derivative, slope of the tangent line. So which one of these has a constant derivative or a constant slope of tangent line? Well, it would have to be this one right here. So this one satisfies A. Okay. The next one says, which one has the greatest initial velocity? So initial velocity, that means initial derivative, so starting just at the very beginning, initial velocity. Now the velocity is the derivative or the slope of the tangent line. Which one of these has the highest slope of the tangent line? So the highest, the greatest slope of the tangent line is the steepest line. And if you look at all these, it would have to be this first one right here. So this is the one that satisfies B. Okay. Now for the greatest average velocity. Now average velocity, remember, average velocity and average rate of change, those two are exactly the same thing. Velocity is just as a specific type of rate of change. So the average velocity, remember, graphically, that's symbolized by the slope of the secant line. So if you look at the starting and the ending points, for example, this first one has an average velocity of 0 because the slope of the secant line is 0. And so if you look at the slope of the secant line here, and the slope of the secant line here, and this one, you would say, well, the steepest line, the greatest average velocity, is going to have to be this one right here. So I'm going to call this one C. Okay. Now, which one has zero average velocity? Well, we just talked about that. And it would have to be this one right here. This one has zero average velocity. So this one satisfies D. Now we get into a little bit trickier territory. Which one has zero acceleration? So the acceleration, remember, that's the second derivative. So which one has zero second derivative? Okay, so you look at all these and you go, maybe you're not sure. Maybe you already know. Maybe you know which one it is. Well, let's just maybe talk a little bit about what other aspects you can look at. If the second derivative is equal to 0, then that means that the first derivative is not increasing or decreasing. What's another way of saying that? Well, if it's not increasing or decreasing, well, then it would have to be constant, right? So in this case, if it's zero acceleration throughout, so if it's always 0, that's what this is saying, then that means that the second derivative is always, not just at one point, always throughout for the whole time, equal to 0. So that means that the derivative is always not increasing or decreasing. Another way of saying that is that it has to be constant derivative. So basically, that's exactly the same as this one, the first one, constant velocity, zero acceleration. So that's going to be E, this last one. Okay, now positive acceleration throughout. Okay, so let's talk a little bit about this one. That means that the second derivative is always positive. So always positive. Okay, so if the second derivative is positive, that means if you go one step back, what does that tell you about the derivative? Well, we said that then that means that the derivative would have to be increasing always. Okay, you actually don't need to make that connection because you have an even simpler connection. If you go even further, you go back to the original function. If this guy's always positive, that means the original function is going to have to be concave up, always. And which one of these is always concave up? Well, it would have to be this one right here. So I would recommend, these are great questions. Make a few graphs of your own and, try to figure out some of these situations and see if you can pinpoint them.